Right now it's recording. So again, piecewise defined functions. We're gonna jump into Desmos. And I am going to, but before we do, before we do that, let me write here an example of a piecewise defined function. And as I promised, I am going to work out some of the questions in the book. So the question in the book I am looking at, and I have my book open here at page 21, is the following. So I'm going to address number 21 from section 1.1. And that question says, here we go, we have the function f of x, and I'm writing on the screen here. So, so I hope everybody can see the screen, folks. If you don't see it, just let me know. And it's given by a couple of formulas here, number 40. Oh, I'm looking at I wrote the wrong number here. I apologize. This page 21. So, so the problem number is actually not 21, but rather 43. So, so this is on page 21 in the book. So, all right, so the formula is f of x equals to x plus 1 if x is less than or equal to -1, and x squared if x is greater than -1. And the question is relatively simple. It says evaluate, and I'm going to write it down here. F of -3, f of 0, and f of 2. All right, and now I want everybody to understand how this goes. Again, this is a review problem, folks. I'm pretty sure you have seen this before, but I just want to go very quickly through this one so that everybody can understand how this goes, and then we'll move on from there. So, so basically, folks, look at this formula here. This is a formula, and figure out which one applies to f of -3. So, so -3 is less than or equal to -1. So this formula here that I just checked applies for f of -3. So we're going to do the problem without using Desmos, and then we'll do the problem using Desmos. All right, so f of -3, if we substitute -3 in the formula here, we figure out that that is equal to, again, we're using the first formula here because -3 is less than or equal to -1, and that's going to be -3 plus 1, which is -2. All right, this is f of -3. All right, the next thing here is f of 0. Now, where is 0 coming in play here? Well, we are going to use the second formula here because 0 is greater than -1. And we plug in the second formula and we get that f of 0 is 0 squared or 0. So that will be the answer for the second thing. And finally, f of 2, and you guessed quickly that we're going to use again the second formula here. And we're going to have 2 squared here, and that's going to end up being 4. All right, so with that being said, we still don't have a good visual understanding of what's happening here because we don't see anything on the screen here, right? So I'm going to do a new share with you, and unfortunately, I didn't open this thing here. So one second, folks, a new share. So let's do a new share right now. Let's see if it works. Okay, there we go. So you get here, you should see this picture with these football players here. All right, so I'm going to go to Desmos.com. And yesterday I was telling you that there is an app for the phone if you are planning to use your phones as a tool. Over here where it says not math tools, where it says resources. All right, so I found somewhere learn Desmos accessibility, I think. Boy, I lost it again. So sorry about that. All right, what is the app? So I found it yesterday and about. All right, about. All right, you know what? I'll find it again and I'll show you where the app is. It was simple, I don't know. So I found it yesterday, I lost it. All right, anyway, so let's go to the graphing calculator. My apologies, I thought I had the app right there. It was obvious, but now it's not obvious anymore. So let's graph this particular function that we were discussing now. I remind you that the function was number 43 in the book. And I'm going to start typesetting. Now pay attention here because there is a trick to understanding how to do this thing here. So I'm gonna type a formula. The formula is a bit longer, so I'm gonna need a little more space. That's why I shrunk the screen. And I'm gonna say here f of x equals, and the formula says f of x is equal to x plus 1 if x is less than or equal to -1. The way things go here, you are going to use curly braces. So I'm going to use, curly braces. Shift here, there we go, curly braces. And inside between the curly braces, I'm going to place the formula. Now the formula says here, I'm looking here in the book, x plus 1 if x less than or equal to -1. So what I'm going to say here, I'm going to say the domain first, the place where that formula is valid, x less than or equal. So simply type the symbol less and then the symbol equal, and that's going to combine those to make less than or equal. And I'm going to put here -1 because that's what the formula says. And now comes the formula. Now, to get the formula, you have to put this colon. So the logic goes that I'm telling the program that x is less than or equal to -1, and for x less than or equal to -1, I'm telling the program what the formula is, and the formula was x plus 1. So I got my first formula there. And then I'll say comma, and I'll do the exact same, I'll use the exact same kind of yoga. So I'll say when x is greater than -1, so I'll say that -1 less than, strictly less than x, that's how you write x greater than -1, colon, and then it's going to follow the second formula that I'm using here, which is x squared. And if I do that, there we go. So that's going to give me, okay, so I have a mistake here. So let's get rid of this thing here. So there we go. So I had an F for whatever reason in front of the formula, and that's going to give us, folks, that's going to give us this thing over here. So this is the graph of my piecewise defined function. And now I can quickly, so is everybody following me, folks? Let me know if you have difficulties following here. So again, the logic that was explained there is a logic to set this up here. You don't, so again, everything is between these curly braces, the formulas. Here's the interval, and here's the formula. Here's the interval, and here's the formula. All right, so the formula follows again. Make sure that you put these. You can always add a space here if you want to make it more visible here. And I'm going to do that just now so that everybody can see. It's the same thing. So that's going to give us the graph that we need. And now if we want to find, like we did earlier, so it says a problem, find f of -3. So I'm going to look here. -3 will be 1, 2, 3 units to the left. And I'm going to look on the graph of f, and I can see that, oops. Oh, there we go. So f of -3 is -3 and -2. However, if you're just curious, what is f of -3? If you want the program to tell you, well, the program will tell you that f of -3, you just types it here, f of -3, and it tells you that it's -2. And if you want to get this on the graph as well, then you are going to have to type -3. Oops. So a point is between parentheses, right? So a pair of parentheses, which I forgot to do. All right, and then you type set here -3 comma f of -3, and that's going to plot your point over here on the graph, and you can click on it and you can see it. Oh, it's f of -3 is -2. So that's how you get the first point. Does that look good, folks? Now you can play with this program, and you can do the same thing for f of 0, for example. If I type set 0 comma f of 0, well, that's going to give me this other point here, which is kind of bluish in my picture here, or whatever color that is, violet or something. So this is the second point. And finally, the third point, which was, what was it? Was f of 2. So 2 comma f of 2, we can plot that as well. It's a black point, and it shows up over here on the picture at 2 comma 4. So that way, folks, we get all the points that I was talking about represented nicely on the graph, and you get your picture as well. So this could serve, this graphing software could serve as a check for you to make sure that you got the correct answer if you run into a problem in the book where you do not even have an answer. So there's a bunch of such problems. So if you ever run into these piecewise defined functions, and that's kind of the first thing that we want to do here, then this is one way to approach the problem. Of course, you can use this on a test if you want. So I'm not going to stop you from doing that, but you need to know how to get to this. So make sure that you understand this, the logic that you use here to kind of graph your function. All right. So, folks, let me know if there are any questions before we move on to something else. So that pretty much wraps up what I wanted to tell you from this first lesson from 1.1. I invite you to do the problems from the book that were assigned from that lesson. Again, there's a wide variety of people here, so with different backgrounds, and I don't know what your specific background is and your interest. Some of you, as we saw, want to take calculus 2 and maybe more than that. Some other folks will finish up with their math requirements once they finish this class. So if you want to dive deeper into these things that were discussed in this lesson, again, this is a review thing. But if you want to dive deeper, just try all those problems there and see if you have any difficulties with any of them. And don't hesitate to ask me in class. Again, I can always address them here. So we have some time, and certainly I can use this lecture time to address problems from the students. So don't be shy to ask questions. All right. So folks, do we have any questions here before we move on to something else? So I'm going to stop sharing this screen. So any questions here before we move on to something else? The screen didn't disappear, so if you have questions on the previous graph, I can always pull it back on the screen, folks. So I'm not closing anything yet. All right, so any questions here, let me know. All right, well, if there are no questions, again, if you feel confident with these things, again, don't, there's no problem, you know, so we're gonna do some more stuff, folks. That's slightly more challenging. So I understand if you don't find this challenging, you know, it is what it is. It is a review, right? So it's supposed to be not so challenging. So I'm going to move on to lesson 1.2, mathematical models, a catalog of essential functions. So I am going to share the whiteboard with you, and we're going to write stuff here. So let's go to the whiteboard. And because my whiteboard is covered partially by another screen, move it around a little bit here. So there we go, folks. Move this around as well. So 1 second, folks, I have to move out some stuff here. All right, so there we go, folks. I'm going to start writing on the whiteboard. So our new lesson here will be 1.2 mathematical models. And probably the important part is here, the last part of the sentence. It says a catalog of essential functions of essential functions. So you remember that we discussed yesterday about functions, right? The various ways to define a function, verbal, right? Description, numerical, graphical, or visual, and then with formulas or algebraic. All right, so today we're going to review some functions. And again, this is going to be a lesson where we focus on this visual understanding of various functions, various formulas that you learned in pre-calculus or in college algebra. So the formulas are as follows. And the first and the most basic function here, folks, they use these. So there's a comment here. Yes, some stuff from these will be on the first quiz. Yes. So who's that? Joe is asking if this stuff is going to be on the first quiz. Yes, there is going to be some small questions from these on the first quiz. All right. So now, folks. I need to make sure that you understand these things, folks. So once we dive into calculus again, this is going to be something that we are going to assume to be known, and it's better to review it beforehand, so that we don't run into all sorts of have to constantly go back and review and review and review. We will review more stuff as we move on, but we don't want to make our the main bulk of our teaching a generalized review. So that's why I'm covering these things, just to make sure that everybody is on the same page at the same common denominator before we move on to calculus. All right, so let's do these mathematical models. So this is just a pretext to review some basic formulas and their graphical interpretation. And the first one is the constant function f of x equals, let's say, so if I'll take your favorite number, I don't know, so let's say that is 3. So what is the graph of this function? Again, you have to, it's a good idea to know how to do these functions without necessarily looking at Desmos. Of course, you can do this in Desmos, very easy, and I'll do this in Desmos myself, but you have to kind of quickly know what this one looks like. And does anybody remember what the graph of this function, if I graph this function, what does it look like? Anybody remembers that? So just tell in the chat, or you can speak to the whole class if you want. So what is this graph if I try to graph it here? So I sketch here roughly, but let's see. Anybody remembers? All right. So let me know, folks. Yeah. So somebody. All right. So all right. It's when y equals 3. Somebody says it's a vertical line. Okay, so well, see, so that's what I thought. So not a vertical line, it's a horizontal line, folks. So yeah, there we go, horizontal line. So very good, Paddy. So horizontal line at y equals 3. So indeed, folks, so this is why we're reviewing these things, to make sure that everybody knows them, right? Yeah. So no problem. That's the reason why we review these, so we can avoid these kind of mistakes in the future. So indeed, this is going to be a horizontal line at y equals 3. So over here, it goes from this point. This is the point 3 on the y-axis. This is the x-axis. This is the y-axis, and the horizontal line at y equals 3 is the graph of this function. All right, very good. So very good. That's the first thing that so I told you. I'm pretty sure that a number of people need these kind of quick reminders, so kind of refresher, before we move on to something more complex. All right, the next thing it says here, so this is the constant function. The second example that I'm going to give here is what they call in the book a linear model. So something like this, 3x plus 2. So if I were to graph this function, what do you think this is going to look like, folks? I just almost told you the answer. So I said the linear model. So you kind of figure out what that would be. But if I were to graph this particular function, folks, Would anybody be able to help me and kind of give me the basic elements so I can actually graph the function? What do we need here? What's the graph going to look like? Okay, you can comment again in the chat, or you can speak to the entire class. It's up to you, folks. So what do you think the graph of this one would be like? So again, it's a review of college algebra if you want. That's it's kind of a thing that we do here. All right, so let's see what is this one going to look like, folks? All right, anybody want to comment on that? Okay, so we got our first answer. A diagonal line, it's going to be a line. It's not necessarily diagonal. So folks, it is going to be a line. Very good. So that's our first. Yeah. So Heinz is correct. Um, so it's a linear line that crosses the y-axis. Okay, perfect. So Sammy basically got one of the well. One of the elements got it right. So here's Sammy says this line is going to go through this point at 2. So this is called the y-intercept, and indeed the line goes through that, and it is a linear function. But what else do we know? So it's a straight line, right? What else do we know? How do I know that this straight line goes this way? Rather than going the opposite way, kind of like this. Why doesn't it go the other way, the dotted way? Okay, so let's see. It's increasing. Yes, increasing, but why is it? Somebody says it's positive. What is positive, folks? Right. There we go. So Nathan got it right. So indeed, there is a slope of 3 here, folks. So slope is this thing here, this number here, 3. This is called slope. And that tells you which way the line goes. So it tells you that the line goes up like this. It's an increasing pattern. And the way the increasing pattern goes, folks, is if we go 1 unit to the right, that's called the run. So if this is 1, if the run is 1, the rise, which is how much you go up, will be 3. So this is very important. So remember that slope, and I want everybody to remember this formula from calculus, from I'm sorry, not college algebra. The slope is the rise over run. So everybody, please remember that. Which means the sketch here is explaining that situation. Are you all familiar with rise and run and things like that? The terminology here. Yep. So let me know if we need to review that quickly. We are going to get back to this situation because we're going to discuss derivative and limits and such, and that's going to come back to us. But once we get it out of the way here, it's going to be much easier to kind of use that a little later. So yeah, that is the slope. All right, so now, folks, slope is very important. Again, so remember this positive number. For example, if an airplane takes off, it's got to have a positive slope, right? Because you don't want the airplane to go like, well, I mean, if it's descending, it goes like that. It has a negative slope. But positive slope means, for every 100 yards that it goes horizontally, the corresponding rise has to be, in this case, would be 300. So when the plane goes 100 yards, if it has a slope of 3, then that's going to rise to 300 yards in the air. So that's kind of the idea with these slopes. Everybody needs to remember this model for straight lines. If you're a little rusty on linear equations and things like that and graphs, please do review those. So there's a bunch of exercises that I assigned in the book and would review just that particular situation. And there's an example in the book as well where they calculate a bunch of rises and runs. So do look at those. That would be example 2 in the section. So now this thing, folks, linear equations, we will encounter several times throughout the remaining part of calculus. It's the basic tool that we use in order to discuss the main notions of especially derivatives and limits. So we will need these. And occasionally now, so now these two here that I pointed out would be a 10 out of 10 in order of importance. So these would be things that you will use quite often in calculus. Now, there's some things that we don't use that often in calculus, but they're kind of nice to know. And I am going to put here a quadratic polynomials, if you want, or polynomial functions, let's say. And those are important for those of you who take especially physics majors or minors. The motion of an object moving in the air is governed by gravity, by Earth's gravity, or anywhere on any planet by the gravity of a corresponding planet, and that motion will always look something like this. So will be a trajectory that's turning up like this, and this is the basic representation of a quadratic polynomial. In fact, this is not the most basic. The basic one is this one here. Is given by y equals x squared. Now, can somebody tell me if y equals x squared opens up or opens down? So do you remember this function, how to graph this particular function? So does it open up, folks, or open down? So there's a couple of answers here. I'm going to pick the last one. Oh, okay. So there's Ali, and he says it's opening up. So indeed, it opens up, and it goes, folks. It goes through right here through zero. I apologize, and my pencil, my drawing pad is not perfect here. So let me try the perfect sketch. There we go. Okay, something like that. So it does open up, folks. This is the basic parabola, and we're gonna do a bunch of examples on that. Now, as you shift things up and down and left and right, and you learn those in college algebra, I'm not gonna insist on that because those, so that used to be something that we used to do very often back in the day when I was in school. There were no the graphing utilities like there is nowadays. And everybody learned how to do these things by hand, to shift things up and down and left and right and things like that. But nowadays, with the graphing utilities available at every place out there, yeah, it's really easy to graph functions like this and derived from this one, from y equals x squared. And I'll give you a bunch of examples. And finally, they are discussing here various other polynomials, and among them the power functions. So this is an example of a power functions. This would be, again, in order of importance for this particular class, this will also be a 10 out of 10. What I'm going to write next is not necessarily a 10 out of 10. I would say maybe a 7 out of 10 or so. So there's power functions. And these are important too, but not as important as the quadratic and linear and such. We will study these, but there is something like this x2vn, where n could be any number you want. N could be 1, 2, 3, 4, 5, 6, etc. But could also be -1, -2, -3, ... and could also be 1/2 or 1/3 or so. And for these power functions, different exponents, this number n here is called an exponent. Different exponents produce different results, and they're quite different, these results. So, for example, when n equals 2, we just studied that is the square function, but when n equals 3, for example, this one, y equals x cubed, will have a nice graphical shape that looks something like this. So you know it's you know the shape is I cannot show you here on the screen, but it's kind of like an athlete running. So you can think of an athlete running. In fact, this is one of the basic example used in computer graphics to create the notion of motion and stuff, the idea of motion by using equations like this and implementing them on a in a computer program. All right, so this is the graph of y equals x cubed, and then you can move on and you can figure out various other graphs. I'm not gonna graph further because we're gonna use Desmos in a few minutes. But you also have functions like y equals x to the negative one. Negative one corresponds to exponent negative one here. So what does this one look like? Well, that's quite different from the one we just sketched above. So if you look at this one here, it's going to look like this. This is called the hyperbola. And you know, this is the a totally different, behavior from this one here. So they're quite different among between, there's quite a difference between them. And finally, and I'm going to put here on the same screen because I don't want to lose this page, there's y equals x to the 1/2. And does anybody remember what function that is in like plain English? There's a simpler way to say that. What is y equals x to the 1/2? Anybody remembers that? All right, so let's see if anybody remembers y equals x to the 1/2. What else do you call this function? There we go, square root of 8, the square root, yes, square root of x. So very good. So we got Nathan and Amber and such. Very good, folks. So the square root function, which has a graph that is totally different from these other two here. So there's a little bit of a variety here that you don't get with the previous functions. Now this one here looks something like this. So it looks like that. And this is a function y equals square root of x. All right. So if you're curious, practice the substitute all of these in Desmos, and you will see, you'll convince yourselves that these are the graphs. But these are something that it's kind of nice to know. So I said that this would be a 7 out of 10 in order of importance for this class. We will not run into these functions all the time, but it's going to be quite often that we see these kind of functions and we study them, for the purposes of calculus. All right, so these are the various power functions. And finally, we have two more things, and I may not have time to do the Desmos today, so I may need to do that next hour. So two more things. So we have rational functions. I'm just going to give a definition of those. So when you have quotients of polynomials, so something like this, folks, f of x equals x plus 1 over x plus 2, something like that. This is called the rational function. These are difficult to sketch. So basically, you probably learned something in high schools, like how to sketch these kind of functions with asymptotes and maybe discuss about y-intercepts and x-intercepts and things like that. We are going to redo these things. So we are retooling everything right now, and we're going to learn a lot of powerful tools to actually deal with this kind of functions in a much simpler way. But for the time being, you really don't need to know anything about these functions other than just the general idea that they have some asymptotes and you can figure things out that way. All right. So one thing, though, you need to remember is the trigonometric functions, and this is the last thing that we do today. Trigonometric functions. And there's three of them that are really important. In fact, two of them are the basic bricks of trigonometry, so there's two of them. And they are f of x equals to sine x. And that's the first function, and everybody needs to know how to graph this function, or at least have an idea how what the graph looks like. And if you took trigonometry, you probably learned about this function. It starts over here at the origin, and it goes up and down as a wave. So it goes like this, and then it goes back like that, and so on and so forth. So it goes like that infinitely many times to the right. And similarly, if you want to go to the left, you go the exact same pattern. So you follow the exact same pattern. All right, so now my sketch is not perfect here, but you get the idea. So this is called a wave function. And because of the obvious appearance here. So remember one thing here. So the sine function always goes through the origin 0, 0, right? So it goes through 0. That's one thing. And the other thing is that this pattern repeats after 2 pi. So everybody should remember 2 pi is the same as in radians, is the same as 360 degrees. Now, in calculus, we will always use radians. So degrees will be just to kind of, if you want to enhance our understanding, but the notions of calculus are built on the idea of using radians, and I will explain you why that is important when we get and calculate derivatives and things like that. So most of the angles that I'm going to talk about here will be in radians, such as like multiples of pi, 0, pi over 2, pi over 4, pi over 6, 2 pi, pi, and things like that. And it's easy to remember again. So the periodicity, the interval of repetition of this particular function is 2 pi. So 2 pi, that's one thing to remember. And obviously it crosses here, the x-axis in the middle, or it also crosses at pi, but pi is a point where things turn from positive to negative in terms of the values of this function. So the sine function is the number one function that you want to remember for calculus. This is a 10 out of 10 in order of importance. So it's not a 7 or anything else like the previous situation. And finally, so I'm going to close with two other functions, cosine x, which looks kind of like this one here, except that cosine doesn't start at 0, but rather it starts here at 1. So cosine starts at 1 on the x-axis, on the y-axis, I'm sorry, and it goes down like this. So that's the graph of cosine. So remember that cosine is a bell shape, at least here around the origin, around the 0, is a bell shape, and it goes through this point through 1 here. And then, so the last one, and this is really the last thing that I'm going to do here, I promise, is the tangent function. And this is the last thing that you really need to remember, just the general idea that the tangent function looks something like this, folks. All right, so it's got two asymptotes. One is here and one is here. This point here is negative pi over 2, and this other point here is pi over 2. So in a way, it looks like the cube function, the cubic y equals x cubed. But the difference between the two is that this one turns straight up and straight down, while the cube function will continue going right and left infinite in infinite directions. So towards infinity, I would say. So these are all the functions. This is the catalog that we need to remember. So I'm going to close the lesson here. Next time around, I am going to discuss how to plot these things on Desmos. Very easy. It's a simple exercise for you, and we'll do some problems from the book here, distinguishing between various functions. So there's a bunch of problems that I assigned from the book. All right, folks, thanks for coming to class today. If you have any questions, all right, so there's a chat here. Our first quiz is next Friday. Yes, correct. That's next Friday. So no quiz this week. Before that quiz, I'm going to send out some practice questions to look over for the quiz, and that should guide you through, the necessary topics that will be on that particular quiz. Any other questions, folks? All right, folks. then I'm gonna let you go. So enjoy the rest of the day, and I hope to see you tomorrow.